Okay, very happy to have Nicholas Carlini agree to give a talk on crypto plus ML. If you know Better Call Saul, if you want to break things in ML, you call Nicholas Carlini. So hopefully, Nicholas will not just tell us about how to break things, but also maybe directions on how to fix things.
Yes. Hi, great. Okay, so yeah, happy to be here and talk. So I'm not a cryptographer, but I'm going to try and talk about crypto. So sorry, please tell me where I'm wrong. I'm going to try and talk about applications of various parts of cryptography towards machine learning, focusing both on the directions that we have done a lot of work on in the past, we the collective community, and also directions that I think more speculatively cryptography could be useful for some more recent things that people are talking about in machine learning that I think this community has not been thinking about and I would like to see more people engaged with. Okay. So I'm going to start with what I'll call, classical approaches. In physics, there's, classical mechanics, and then there's the modern stuff. And I think you can think of machine learning basically the same way. I'm not going to spend almost any time on there's privacy-preserving inference. This is the classical approach that sort of takes cryptography ideas and applies them to machine learning. The idea here is fairly simple. You have some machine learning model, you want to perform inference on the model so that I don't learn anything about your data and you don't learn anything about my model. We do some kind of MPC or fully homomorphic something, and then we sort of manage to, as a result, compute the outputs correctly. And this works, and people have been working on it for a long time. I don't know anything about this field, but when I talk to people about crypto and machine learning, this is one of the first things that people sort of jump to. I'm not going to talk about this at all. But this is sort of the style of thing that I'm thinking about, and I want to try and encourage people to work on sort of more diverse things. So, not that. The other thing that people leap to when I talk about crypto and machine learning is privacy-preserving training. So instead of privacy-preserving inference, where the question is, can I compute inference on private encrypted data? Here I'm asking, can I learn some property of the data without leaking too much about the details of the training data I'm training on? The attacks here are ones that we've shown in the past before. If you take language models that are normally trained on just whatever text that they have, it turns out that the models just memorize all kinds of random stuff from the training data set. This is bad. It works not only on language models, but also on image models, where we've shown that if you could train diffusion models, this was an image from the training data set. This is an image that we reconstructed just querying access to the model. Again, this is not a very good thing. And so there are lots of approaches that apply techniques from cryptography, mostly differential privacy, that try to make this something that you can guarantee is not going to happen. This paper has 8,000 citations or something. Again, I'm not going to talk too much about this as a direction, because again, it's sort of one of the things that I think people understand pretty well. The other area, sort of Shafi very briefly mentioned, there's these proofs of robustness. The question here, again, this is one of the classical problems people have studied pretty well, is I want to guarantee that my model is robust. So I have some model, I want to make sure that if I make small perturbations, the model still gives the same answer. And again, people prove with basically one of two ways. One is they try and reason sort of mechanically about what's going on through the parameters. They try and bound the sensitivity of the function and show that if you perturb the input by a small amount, the output is going to be guaranteed not to change because you can trace through the activations how sensitive each layer was. The other approach people take tends to basically be differential privacy inspired, that if you add a bunch of noise to an image input and you do this many times and the output hasn't changed very much, then you can be fairly confident that smaller perturbations also would not have changed the answer. Okay, so these are sort of the things that people have done much more classically, that there's a lot of work on these directions. And what I'm going to try and do is not say we shouldn't do these things. Obviously, we need more work here. We're not done. We haven't solved any of these problems exactly. But I want to sort of pose a couple of new problems that I think people have spent a little bit less time working on that I think are particularly interesting to me. Okay, so I'm going to start with things that sort of are semi-classical approaches, but like are a little less so. And then I'll maybe spend the last 15 minutes or so on some sort of much more speculative stuff. Okay, so I should mention, please stop me at any point. Happy to take questions whenever you have them. I'm going to talk about some pieces of technical work and some just ideas. And so any time if you want to ask questions, happy to take them.
So
Yes.
you mean where you know the attack, like the perturbation class, and then you protect against that.
Sorry, by classical I meant something like, like classical mechanics, like just like things that we've been studying for a long time that like have been around, and everyone basically, I assume everyone here has basically seen, seen these kinds of things. Like there's nothing like, there's a lot of work to do, right? Like, like these things don't actually like fix the problems entirely, and there's a lot of stuff to do, but like it's like fairly well studied. We know what we're trying to do. And what I'm going to try and now talk about is like things where we sort of we don't have it pinned down the problem quite so nicely. Okay, so watermarking is like sort of maybe halfway in between. Watermarking wasn't the topic. Okay, by watermarking here, what I mean is watermarking the output of generative models so that we can detect that it's generative, the output of a model. This is not something that people talked about, let's say, 4 years ago. Like, it was sort of a thing that people have really started to work on, like maybe really in the last 2 years, this became a big hot topic. I haven't done that much work on it, and there's a lot of really hard theory stuff that I don't understand, but I want to call attention to it because I think it's a particularly interesting problem for people to be working on. And what I'll do is maybe just introduce you to like the most naive version of how these things work, and then there are like much more fancy versions of it on top of that. So text watermarking, at least, most of the schemes work something like this at a high level. They take each word that's output of a language model and they color it red or green. And sort of half of the words in the English language are red, half of the words in the English language are green. And because in English you can substitute one word for another relatively easily, what they do is they sort of, there's no good reason why in normal text, red words should follow green words more often than not, right? Sort of like, if you just like actually sample the two sets randomly, you would expect that on average, you get like a switch basically mostly every other word or something like this. You can like model the distribution. And what they do in order to watermark is a very simple trick. When it's generating, if the previous word was green, then with some somewhat higher probability, make sure that the next word that you generate is also green, and vice versa for red. And what this means is that when you have text that comes out of a language model like this, you'll have long strings of green and then long strings of red and then long strings of green, with like higher probability than random chance. Okay. Now, okay, this is not exactly what they do, because if you do this, you lose a bunch of utility. So, you're not gonna guarantee this. You'll make it happen with like somewhat higher probability than random chance, and you're not actually gonna have red words and green words. You're gonna have them dependent on some hash function and a bunch of fancy stuff going on behind the scenes. But like, core idea, this is what's going on, and this lets you detect whether or not you had some word that was, or if your sentence was generated by a language model, because you can just run a hypothesis test. How many transitions are there from red to green? And the probability of the watermark is like I don't know, this is the wrong equation, because this is not a probability distribution, but like, something like you count the number of transitions, and so this is watermarked. And so I think the questions that people have been working on here are very interesting. The main question is, how do you make this robust, and how do you make it indistinguishable? And people have done a bunch of really good work there. And one of the things that I'm really excited by seeing more of is, how do I make this robust, not only in like pathological sort of like crypto definition settings, but in the real world. Suppose that I took this text and I asked a language model to rephrase it. This is like the most trivial attack. How can I get robust? What does the robustest argument here mean against this as a class of attacks? This, I think, is one of the biggest open questions that we've been trying to think about in this area. One of
model to rephrase it, or
yes, yeah. So what I do is I have some really smart model that's watermarked that like answers my question for me, and then I go to an open source model on my own machine and say, that's the answer. Please just like give me the text. Like a student wants to cheat at their exam, so the smart thing just gives a solution, and then like the other one just like does the thing, or for spam or whatever else you want. This kind of approach.
Wait, why don't they go to the other one to begin with?
So the big giant one, because the small one is too dumb to give the answer. Like it can summarize and it can sort of like rewrite, but it's like it can't solve whatever mechanics homework you have. Okay, and so one of the directions that I think people have started to think about is what are called semantic watermarks that try not to watermark the individual tokens, but try to watermark like the idea that has been generated somehow. I don't know what this means, and most people who talk about it don't have very precise definitions. I think this is one area where crypto would be, I think, nicely suited to try and come up with some formalization of this. Okay. Okay, so another topic I'm going to talk about, I'll spend a little more time on here because I've done a little bit of work on this, is on model stealing. So the basic question here is relatively straightforward. We have some machine learning model. Oh, sorry, yes, please, go ahead.
I mean, what's the punchline? The punchline is we don't know, or sorry?
The punchline is, yeah, we don't know.
Sorry.
This is for which?
So you just said, okay, let's ask the other thing to rewrite it. So does it?
The attack works and it breaks these things often. Like, I mean, like, okay, so there's some robustness and there are schemes that sort of claim a little that it's hard, but like in the limit, these attacks are just very, very powerful. And like most papers evaluate robustness against this, and they evaluate against like number of rounds. But the problem is that like if you ask the language model just to rewrite, it doesn't do a very good job. But there are more clever attacks that, for example, I'll initially ask for the smart model to give me the output in French, and then I have a translation model that translates to English. And now things like entirely break. There's like some classes of attacks that work like this, and this I think is like the main category of attacks that I'm interested in to see if we can do anything about. And yes, the punchline is I don't know what works, and I'd like to see definitions.
Do you know a meaningful semantic similarity metric?
No.
How to define what semantic similarity means, like humans? I mean,
Yeah, how do we define things? I don't know. That's your cryptographers. You do definitions. Yeah, I don't know.
Semantic similarity is your question, right? Semantic similarity is
sure. Yeah. Right. You can come up with different distance metrics, and yeah, I don't know what to do here though. Yeah, it's like there's a reason why people haven't fixed it. It's because it's hard. But like I would like to see.
I mean, people are working on it.
Yeah, they definitely people are working very hard on it. I just sort of want to call attention to this as like a problem that I think in comparison to like LP robustness on image classifiers, where like we know what we're doing. We sort of have figured it out. We got the definitions. Like with people, there's still a lot of work to be done. But like the problem is very nicely scoped. This problem is much less nicely scoped, much harder. It's much more ambiguous, and it's much more timely. So that's why I sort of want to call attention to this. Yeah, go ahead.
Do you have some thoughts on if the attack you're describing is similar to the watermark or do you have thoughts on what potential realization you will?
No, I don't. And yeah, yeah. The question is, do I have any thoughts on how to do anything? I don't. I would like to see, like, I sort of, there's a bunch of really good work, but I'm looking at it, I'm like, I just don't feel satisfied. Like, it feels like there's something that someone could do that would like really feel good, and I just haven't seen that. Yeah.
From what I recall, there are like watermarkings that are robust against like small entities, right?
Yeah, but small, yeah. So this is the thing that's nice and easy to prove about. You can make watermarks robust to small edit distance. Like this scheme, for example, as I described here, like is robust to small edit distance kinds of things. There are lots of other ones that you can throw like this, but the students are not going to do like whatever like small edit distance. They're going to do whatever thing works. Or like people who are sending spam are going to do whatever the thing is that works. And if have another language model rewrite is an attack that works, or things like it, like this is what they're going to do. And so I think watermarking has sort of solved the easy class of problems, but has left open the much more ambiguous case that is ambiguous and much harder to make definitions on. But like, I sort of want to encourage people. It's nice to work in small little toy areas where all the definitions are clean, but in practice, the world is messy. And so like we should also spend some time there, even if it's not like nice and clean.
So do you have a conjecture? Do you have a conjecture about the semantic similarity from your experience? Did you make it impossible to watermark, right? Because it seems like you're implying it's impossible.
Yeah, I mean, I don't know if it's impossible.
Distance is possible, right?
Sure. Yes. Okay.
So, yeah.
Is it impossible? Maybe. I don't know. I like to break things. I feel like it's probably impossible, but like if you make a list of the number of things that crypto can do that I would have said was impossible without hearing about them first, it'd be quite a long list. And so I don't know, it just feels like maybe it is something.
Definitely impossible for some definition.
Yeah, under some
I guess
definition.
the question is, can we define something meaningful that is possible?
Yeah, exactly, yes, yes.
It's definitely, there are many impossibility results.
Oh, there is one? I thought
Yeah.
there was a set.
Would you be happy with progress that is impossibility results?
Yes,
You
yeah,
would.
yeah, that seems good, right? Like, we should know, like, I mean, in the limit, I want to know because some people are gonna like say, you must do this. But like, if we can just say like, that cannot be done, that's just a useful thing to know.
It's one nice thing about the impossibility results in space is that they actually give you a fact which you can use rather than just saying it's impossible.
Yeah, that's good. It's much easier to understand those.
But he gave an attack, right? The translation is an easy attack
Yeah, but
that
saying
just breaks everything.
just any scheme, there's an attack.
Okay. I'll talk a little bit about model stealing, which is this thing that people have been thinking a lot about recently. Okay, so in general, there's two variants of model stealing. There's a variant of model stealing which says, I want an approximately similar model to the one that someone has deployed that's like mostly good on the data distribution. And this is a very hard problem to do anything about because basically you just make queries and then just fine tune. And if the model is any good, then just the fact that you can make queries is like this, you can just fine tune on the outputs of the model that I have, this high quality one. And you use this as a good labeling oracle, and it's like a very hard problem to do anything about. Lots of people are working on this. I think this is maybe a very important question, but I don't know how to do anything about this. So I'm not going to talk about this. I'm going to talk about another problem in model stealing, which asks, can we actually steal the exact model that you're deploying? Yeah, question, yes.
I was gonna ask, I've seen some that you're actually leaking out weights, and some where you're basically using a model as like a training oracle.
Yeah, okay, yes. So yeah, so I'm not gonna talk about the training oracle kind of approaches. I think they're good. I haven't done work on that space. I've done work on the other side, and I'm gonna talk about the like leak the exact weights version. Okay. And I want to think about this for two reasons. One is, it feels like it should be possible, but it's been very hard. And so I would like to get like somewhat more confidence that like it's actually really hard, because if you could do the exact thing, then obviously we would just want to do that. And so I would like to understand like what are the limits of what we can do in the exact case, just so that I sort of get some level of sort of empirical robustness. In the same way that, you know, we don't have some proof of robustness for AES. Just like a bunch of cryptographers tried really hard and we can't break it, is sort of the argument there. I would like to get some level of like empirical robustness to like these kind of model stealing things. Like it's not a thing that I should have to worry about in the exact case at least. Okay. With that said, we can make it work for small classes of problems, and that's what I'm going to talk about for a little bit. And then I'm going to talk about a little bit of work on making it work on giant models. Okay, so these are some papers at Crypto that we've been working on. So very theoretical. Sort of let's assume that we have a neural network that has ReLU activations and is small. I don't know, like thousands of total parameters, something like this. Hundreds of thousands, maybe, definitely not the big giant models we're actually using. Let's also suppose that you're only using what's called the ReLU activation function. It's an activation function that just like, if the input is negative, it clips to 0. If it's positive, it stays exactly as it is. It's like max of x and 1. So we have a neural network. The neural network basically got inputs. You take the sum, you take the ReLU activation, you go layer by layer by layer, and this is exactly what you're going to do. And the question is, in this case, where these parameters are the things that I've learned, can you steal a copy of this network on my own machine? Okay. So first, trivial impossibility result. I can take this network and permute these two neurons, and the function is the same. Okay, so by definition, you cannot steal the exact weights in order. You can also multiply this layer by constant 2 and this layer by constant 1/2, and you get the same function.
Wait, why do you care about exact?
I don't.
answer?
Yeah, but sort of, I don't, but so what I'm going to say is what I want is I want functional equivalent extraction, not like bit for bit weight extraction. Yeah. Okay. And what I'm going to talk about now is a reduced round attack sort of crypto style on one hidden layer networks. And then I'll just like claim that it works for deeper things. But if I wanted to talk about that, it'd be another like 10, 15 minutes. I don't want to go into too much detail. I just want to give you a flavor of what this looks like. So let's suppose that we have a really small model, 2 inputs, 2 inputs are nice because then I can graph it on the plane. 3 hidden neurons, and then 1 output. So what I'm going to show you here, this is an entire characterization of this neural network. What I've done is I've color-coded each of these regions according to a unique color for each linear region of the model. Okay, what do I mean by this? I can sort of point individually to neurons in the model. So like this middle neuron corresponds exactly to this line. What this means is when you're in this region, this neuron is negative. When you're in this region, the neuron is positive, or maybe vice versa, I don't know. And similarly, for all of the other 3 lines, we have the exact same property. So we've just divided the space according to these 3 lines that we've drawn through space. And the reason why these lines exist is because like this is like sort of all combinations of how you could assign plus and minus to these ReLU activation functions. How's this going? So far, so good? Yeah, okay. So it turns out that what you can do is if you sort of zoom into like one part of the region here, suppose that I was on, okay, okay, good. So in this linear region, these 2 neurons are essentially dead. What I mean by this is because if they're in a negative region here, it's almost like they don't exist. The weights output here, the activation output here is exactly 0. So this is the only neuron that is doing anything. And so that's sort of what's making each of these linear regions. And so the visual thing to notice is that like the location of, I'll call these like critical hyperplanes, like basically completely determines what the function is that you're using. So like the only thing I need to do in order to steal this 1-layer network is to figure out where these critical hyperplanes are. And doing that is actually relatively easy. All that you need to do is you need to like walk along the input. Let's suppose, for example, I knew this point was on the boundary. Let's just assume that for a second. I just need to compute the normal vector here. Like say take a step, see what the ratio of these 2 values is, and this will exactly tell me the direction of this hyperplane. So a little bit of math of how this actually works. So you have some inputs x and y. I know this input is 0 because I'm like on the boundary. And so what I do is I take a small perturbation and I add x plus epsilon over here. And this sends me to some point where I'm not sure what this value is here. And then I do a small x plus delta, and I find the delta so that this brings me back to 0. And now what I know is true is that I'm back on the decision boundary. And so I can conclude as a result that if I had these 2 weights and I called them A1 and A2, I could like exactly say definitionally like sort of this relationship holds true. Like because I've added a small amount, and so I multiply that by this 1 weight. I added a different amount multiplied by the other weight. So if you just rearrange terms, you get this. So I can sort of learn the ratios of these weights in this model. Okay, so that's good. What we've learned here is we've learned the normal vector. What I don't learn is I don't learn the magnitude of the vector. And it turns out that actually the magnitude up to scaling isn't important, because as I said earlier, you can multiply 1 layer by 2 and the next by 1/2. So like you can't do anything about that. But one thing you do learn that's important that you miss out on is I don't know whether the direction points positive or negative. And it turns out this matters because ReLU is not symmetric. It's negative, it's 0 on the negative region and positive on the other region. And so you have to do something to figure out whether or not you go one way or the other. And this is a little bit tricky and is basically like the hard problem in this whole thing. And I'm not going to tell you how we fix this. And in general case, in this simple case, what you can do is you can just like actually read off the value of a couple different locations and just like some guess and check kind of thing. You solve some numerical equation and you can figure this out. It's a little expensive, but like it works. I'm not going to talk in details about how this happens though. So this is the flavor of what we try and do in these kinds of attacks. The one thing I haven't told you so far is how we actually learn these points on the line. That actually is relatively easy. All I'm going to do is I just take some vector cutting through the whole space. with overwhelming probability, this is going to intersect at least once or exactly once with every single neuron. And the way I can identify this is what you'll find if you just plot this. I'm plotting now on the y-axis the actual value of the function. The function will change sign, or will sort of bend exactly 3 times, corresponding to each of the 3 lines that you're cutting through the space. And so you just need to query the model a bunch of times and then check where has the gradient changed. And those are the points of the critical values. Is that a question?
Yeah, so this seems to require you black box access to the model, but what if I only give you an example?
Okay, so this is, yeah, so what this requires, I need black box access, but I need soft outputs. So I sort of, the outputs need to be like, you know, floating point numbers in some way. The question is, can we do this if I only know, like, this was a cat, this was a dog? Is that the question?
No, if I only give you examples that like drawn from some.
If you don't get query
you
access
cannot
with
control
random
what the
examples.
inputs are.
If I can't, I see. Okay, so this is a chosen plain text attack in some sense. I have to be able to choose them, and I have to be able to make epsilon perturbations of the inputs, which is often the case for image models, is very much not the case for language models. Is that what you're asking?
Not exactly.
Not exactly. Okay, ask again.
Are these attacks also working? Are some of these attacks also work just if I get a bunch of examples? I don't get to control the examples.
Yeah. Okay. So yes. So the attack is chosen plain text, not known plain text. So I need to be able to choose the examples adaptively. If you only give me a list of examples, then this does not work. Yeah. Okay.
And can you answer the question you thought he asked about the floating point?
Yes. Okay. So there's a separate question of what if the output is I only know the decision and not the actual values. We have a paper at Eurocrypt from a month ago that shows that we can do this. So if you only say cat versus dog, it turns out you can still learn how to do this. I don't have any slides on exactly how to do here, but essentially the idea is that if you walk along the decision boundary, you can still compute the angles of these planes if you do more clever stuff. Like it sort of doesn't fundamentally stop me from learning the angle of the decision boundaries, but I don't have anything to talk about there. Like the details get pretty messy.
Model stealing is different from like model recovery. Like I remember, you know, I don't know, 10 years ago, they were saying, oh, any black box access to any classification model, you can reconstruct a model that behaves the same.
Yeah, so
It's not this?
So this is the same problem. So people call model stealing, model extraction, and model recovery roughly the same problem. And so I don't know 10 years ago what they would have been saying for black box
There was
access.
some invited talk by David Wagner and some CCS, and he was saying that, but I don't.
I see. Okay, so this was talking about. Oh yes, okay. Okay, so I do remember this. This is talking about the non-exact version, about the like if I can make queries and I can do a learning-based thing,
Right.
I can learn a copy of the model which behaves
Exactly.
awfully similar, and it's not exactly the same, but on the distribution of data that I make queries on, it behaves roughly the same kind of function.
Got it. And here you want to say.
I want the same function. Yes. Yeah. Yes.
Would it be interesting to somehow make these queries in a fashion where it's a little more undetectable?
Yeah, this is because one of the common ways people can defend against this is I check, the query pattern here is pretty suspicious. And so, yeah, you can try and do things to try and make this much less suspicious. Yeah. Okay. So, great. So this is, okay, sorry, was the question?
Different question. Like,
Yeah.
what would happen if you just try to train the model on data?
Yeah, so that's what that's the inexact people try and do. So the inexact stealing tries to make queries of the oracle and just train the model to be similar. And what happens empirically is all of the decision boundaries are entirely different, but like on the local region of the data points that you've made, it assigns roughly similar labels most of the time. And if this is good enough for the attack that you want, is sort of task dependent on what the attacker wants to try and achieve. Okay, so this style of approach, where I'm gonna like make queries in this way, do gradients, has a lot of limitations. Like I need high precision math to be able to compute these normal vectors. I need only value activations. I need the model to be pretty small. It's never gonna scale naively like this to large transformers. And so last year we wrote a paper trying to ask like, okay, let's give up. Oh, sorry, go ahead.
I think you lost the slides.
No, I don't. I'm
sorry.
just talking for a second.
Okay, sorry.
So last year we wrote a paper where we tried to answer this question and say, okay, like let's suppose that we are going to give up on the exact thing entirely. Like, what's the sort of middle ground we can try and get if we want to try and get some of the model? Okay. Okay. So what we're going to try and do is we're going to try and do exact extraction, but for only part of the model. So in particular, what I'm going to try and do is we have a transformer. This is some big, giant, ugly function f of x. And what I'm going to try and do is I'm going to try and steal this layer. It's only one layer. It's not very much. But I'm going to try to exactly recover these parameters for no good reason. Like, like I can write down some reasons maybe why you'd want this, but like because we can. And like what I would like people to try and other people to think about is like, could we do other things? Like, could someone steal that layer? Can someone steal like, the ratios of these things? Like, I think it's interesting to ask, like on real models, can I learn a little bit less, but still do this exact question? Here, what I mean is up to invariances that you can define with the model, they're the same object. So it turns out in transformers that you have some invariance for the rotation of the matrix in some way. Up to this kind of affine rotation kind of thing, I'm going to learn exactly these parameters of the model. Floating point precision, they like more or less like, up to some invariance, yeah.
It's the representation or the functionality?
Yes, so in this case, I will learn what is the functionality, which is equivalent to saying the representation up to some rotation. Basically, because there's a linear layer here and a linear layer here, you can and because it's not so ReLUs like distort the space and bring you into the upper sort of region because it turns out what people do is they do an L2 norm preserving operation, which means that you can take an arbitrary rotation matrix here and the inverse rotation matrix here, and they behave identically. You can multiply things through. So I'll learn like this up to matrix multiplication. Okay, I'm not going to talk exactly about how to get this done. Instead, let me just like give some intuition on how you can learn at least some piece of information. So what we're doing in a transformer is we query the model, and we have some inputs, and what you get is, okay, again, I'm going to assume that we get logits out of the model. What this means is I'm going to get for every single token in the vocabulary, how likely that token is to be the next token given the input that I provided. It turns out that you can get this from real production models. I'm not going to talk about that. Just take for granted this is a thing that you can do. I can read off the exact sort of token probabilities for every token in the vocabulary if I give an input query. There are often, 100,000 tokens in the vocabulary, and so I'll read this off, and this gives me a 100,000 dimensional vector when I make one query on the input x. And so what I'm going to do is I'm going to repeat this many times and make n different queries. And then I'm going to construct a matrix here. This matrix is going to have, I'm going to call it Q, and this matrix has the number of columns, roughly n, number of rows, roughly n. And so a simple question you could ask is, how many linearly independent rows does this have?
These X's are random?
Yeah, they're random, yes. Yeah. So this I sort of, is just randomly pick these things. And so you might expect, I'm making random queries like this n by n matrix, random data. It should be mostly, n linearly independent rows. Okay, just for numerical stability reasons, I'm going to ask for non-zero singular values. Exactly the same thing, but just okay, I'll like mostly non-zero because floating point math is hard. Okay, so what I'm going to do is I'm going to show you what happens as I add more rows to this matrix. So I'm going to query the model a bunch of times, and I'm plotting here the sorted value of the sorted magnitude of the singular values. So as I make more queries, at each number of queries, you have roughly the same number of singular values, and everything looks pretty normal until you get to some point here, where all of a sudden it looks like there's like only 2048 non-zero singular values, despite the fact that I've made, and I have my matrix has 3,000 rows. Okay, so what's going on here? Sort of why is this happening? The answer is what was that? Yeah, that's the dimension. Yes, exactly. So we have some ugly function here doing complicated stuff. I don't understand what it is. let's call it h of x. What we're doing is we have h of x times this last matrix A. If we write down the shapes of these kinds of things, this thing goes from H to some big giant 100,000 dimensional thing, which means that this is like an up projection matrix. Logits are 100,000 dimensional vectors, but they actually lie in an H dimensional subspace, because that's how the model is working. Internally, it's working in some H dimensional space, and then it up projects. And so I can recover the entire sort of H dimensional, I can recover this thing up to, again, a rotation kind of thing that's going on here. Okay. And so I'm gonna skip just a couple of slides for a second. It turns out that because of this, you can learn not only the value, you can actually learn, not only the number of singular values, you can actually learn the whole function. So this is like a thing we could actually do on real models. So like we ran this on an actual model. We ran it last year. We ran it on a bunch of OpenAI models that had this API. And we could write down like exactly, the sizes of the models, and we did also stealing the parameters, where I was at Google. It is very hard to be like, please OpenAI, can I please steal your data? Now they were pretty nice. They said yes, but Google lawyers were like, under no circumstances can you have OpenAI model weights on Google servers. So like, I actually couldn't implement some of these things exactly as much as I wanted to, but like for the versions of it that we could implement, it actually worked pretty well. Yeah. So yeah, for like this was for Ada and Babbage, $4 and $12 for those ones for the one layer. Yeah.
Mostly on the responsible disclosure, why is the dimension sensitive to OpenAI? It seems like it would just be
because they don't disclose it publicly. And how big the model is has something to do with how much they should actually be charging versus what they're actually charging. And you can look at like okay, so here's one thing I can say. So these two models are both called Babbage. They have roughly the same performance. This model is smaller than this model. What I have learned, OpenAI has figured out some trick to make this model smaller but have the same performance as this one. If you knew, like you could track the sizes of the models over time, you could learn something about what kinds of tricks they had behind the scenes. Like, should this be private? I don't know. But they declare it to be so. And so, yeah.
You can discover this for $1,000.
Yeah, and you can do this. Okay, so they implemented defenses that prevent this kind of thing after we sort of told them about this. There's another paper out that sort of concurrent with ours discovered basically the same kind of trick. And they report some numbers in their paper of how big that they think that this is. The agreement that we reached with them is that they would tell me that I am right, but I could not put it in the paper. So I can tell you, like I ran the attack, I know the number, but I can't tell you exactly what it was.
How about the talk?
What was that? Oh, how about the talk? In a recorded talk, I don't know. But yeah, okay. Okay, so that's all I'm gonna say about model stealing. I will say though that like, okay, so yeah, go ahead.
If I can obfuscate the neural network that you that I train, can I say that?
If you obfuscate, meaning like like I/O, like sort of that kind of thing. So what does obfuscation tell you? Obfuscation says that you cannot learn anything more about the function than can be observed from input-output behavior.
Yeah.
He's only doing it.
And I'm only doing input-output behavior. Therefore.
But you're learning the dimension of the.
But I'm only querying input-output behavior. So obfuscation.
For example, I can have two networks that have different dimensions that have the same input behavior, so you don't know which.
But empirically, this is not true. So empirically, if you had, so it is possible you could have two networks that have this. So I guess what statement I'll make: if two networks have the exact same input-output behavior, then the hidden dimension size is the same.
Because you assume a certain structure.
Assuming the structure.
Black box within a certain class.
Yes, exactly. Yes. Yeah, because I'm assuming a certain structure. It's possible that you could write down, an arbitrary different function I didn't know that was obfuscated. I couldn't tell the difference. But if I think that you're using a transformer, then I can tell you the properties about it. Yeah, and so this is, I think, one of the things that's like an inconvenient thing about obfuscation plus neural networks, is that what obfuscation tells you is that you can't learn anything more than can be deduced from the input-output behavior. What can be deduced about the input-output behavior? Potentially everything. So like, has obfuscation actually done anything for you? In some sense, no.
Quick question.
Yeah.
Did they have to change their API?
Yeah, so they changed the API. in order to prevent us from, I declared that we could learn the entire logic vector by making queries. They made that step impossible. Or they made that step maybe 10 times or 100 times more expensive. And this goes to like a very classical security kind of thing. They think that there's a dollar value associated with this information. Once the cost to learn that is greater than the value associated with it, like they think that they've done a good enough job. Feels fine. Yes.
So once you store it.
Yeah.
What are you gonna do with it? Let's say
Yeah.
your own model, yeah?
Yeah.
Can you tell them that it's that one?
Yeah. So can you tell if it's the same one if you stole it? So some people are thinking about watermarking for models.
Right.
And this is another interesting area where like you want to answer this question. There are approaches that try and do this, but I haven't talked about those at all. Another good direction.
So they can sort of subtly put in something that when you steal, they will be able to detect.
Yes, exactly. So basically what you do is you sort of move the decision boundaries in ways that would not have happened by random chance.
Mhm.
And then you can show, look at your model, it has these weird decision boundaries that matches up exactly with the output of my hash function. And the probability of this happening by random chance is 0, therefore you have stolen it. And then you have to worry about what if I steal your model and then perturb the weights by a small amount so that it doesn't exactly match. And so there's the whole game over there. Okay. So this is where there's like been a lot of research. But like I'm a little bit less excited about like all of the things I've just spent all my time telling you about, which is like I've written a lot of papers on them. But like I think like this is a thing that like is very important work, and like I will continue to do working on it. But I would like to see a little bit more work on a couple directions that people are just starting to think about now, especially from this community, because it's things that people are like just starting to get started on. They feel like they have a crypto twist, and the people who are thinking about them are not crypto people, and so I'd like to have more of you thinking about this. Okay, so caveats that, yeah, me, not cryptographer, I would like to sort of get your thoughts on this, and if you tell me it's like not a problem for cryptographers, then like that would be good for me to know. Okay, I'll call these like the modern things that people are trying to do that like feel crypto heavy. Okay, so this thing that people are trying to do that is the following. They're going to try and create a model that cannot be fine-tuned. Okay, what do I mean by this? People are worried about models being dangerous. Like maybe the model could have the ability to perform some kind of thing that like helps someone produce a bioweapon or something. So yesterday, Anthropic launched Claude 4, and as part of this, they declared that the biggest model had enough of an uplift on some trials that like it might be able to help people produce bioweapon kinds of things, and so they like have put in protections in place. And in the future, people are like trying to do more and more of these protections to make sure that people can't use models maliciously. This is very hard to do if you have a white box model that people can fine-tune themselves, because you'll put all of these training measures in place so that the model will refuse all your harmful questions, and then someone just like fine-tunes it to like answer them exactly, and then like you've lost all your protections. And so there's a research direction. I'll skip this. There's a research direction where people try and create models that cannot be fine-tuned. So that step 1, I will make my model refuse to answer certain kinds of questions, and then step 2, I make my model unfine-tunable. And the idea is now my model is safe. Like you can use the model, you can query the model, but you can't change the way that it works. Okay. Turns out these proposals don't work. So these proposals are doing like weird learning-based things that try and make the gradients ugly. And it turns out that there are some really simple attacks that we had in the paper about that was at iClear. Really simple, I really mean really, really simple. Like if you just run the attack multiple times, like it just works. Like this is like, it's not good, like it's sort of like.
So you can't fine tune.
So I can fine tune, yeah. So the model they claimed was unfine tuned. Okay, so let me explain this plot in just a little bit of detail. Initially, what this y-axis is showing is accuracy on some dangerous set of questions. They just declared them to be dangerous. The original model is at 70% accuracy. When they fine-tune the model to refuse and then make it unfine-tunable, it's down here at 25%. That's random guessing. So this model is like not harmful. This model is harmful. And they claim, and when they run the attacks, that like the sort of attacks cannot do this very much. But if you just run the attack multiple times, the margin of error is quite large, and the attack actually just works some of the times. Okay, so this is like not a very robust fine-tuning prevention scheme. And there are a bunch of other attacks that I'm not going to talk about too much. Turns out if you re-implement the attack in a new code base, the attack just works. This is because they did some like adversarial training against a particular implementation.
When you say attack, you mean something that does fine-tune?
Yeah, it does fine-tune. It correctly fine-tunes. And if you just like re-implement this in a new code base, it basically works because they adversarially trained against one particular code base, and what it learned to do is to like defeat the way that that particular implementation exactly in the details was working, and just a new code base that made it work the same way. Okay. So there's a bunch of things you can also do. I'll skip most of these. And so I guess what I'm wondering is like, I don't know, this feels kind of crypto-like. Like it feels like, I don't know, a little bit like IO, but like not exactly. Because like I'm not like asking for a lot of the properties, but like I kind of want to, you know, mess with the activation so that you can't do it. But like, I don't know, is this a thing? I don't know. Yeah.
So can you just tell for like non-AI people, what do you mean by fine tuning? Do you mean like a human, like there is a protection, you ask a query, the query doesn't ask, and you try to ask more?
Sorry.
It's automatic, take something, some computer works and gives you a model.
Yeah. So what I mean is like train the model more. So you know, like you how do you get a model? You start with initial rates and initially random weights. You train the model, you adjust the weights until it answers your questions correctly. All I mean by fine tuning is do more of that. Is like edit the weights more, like with an algorithm, gradient descent on the weights so that it answers the harmful questions.
But not like given access to a model with protection, you build some kind of interface, like I ask a question to the interface, and the interface basically asks like 15 questions.
No, I don't mean this. What I mean is,
Yeah,
so that also might be possible. People, that's a separate area of work that people try and make that not possible. So there's like the question of like, if the model is static, can you ask questions maliciously? That makes the model give you the answers. That's called jailbreaking. And there's a separate question of, can I take the model itself, the model parameters, and like edit the code of the model so that the model now answers the questions that I wanted.
But semantically, isn't the second approach a special case of the person? One way for me to do it, to fine tune the model, would be to kind of build some kind of little interface that asks my questions and just, oh, you're saying that's how.
So the first is actually, a general purpose. So when I can edit the weights, this is a more general class of attackers than the attacker who can only make Oracle queries. So, you know, like in one case, I can only make Oracle queries of what's going on. In the other case, like I can, you know, do a related key attack or like these kinds of things. Like there's more things that I can do in making queries in order to see what's going on.
It seems like they're incomparable because in the fine tuning that you define, you restrict the model of computation to these bizarre things that nobody understands these weights.
Yeah.
I'm saying I can do Yael's thing or whatever. I can do whatever weird non-LLM things on the outside. But you're saying LLMs is more powerful?
So when I say I'm allowed to do fine tuning, you're allowed to edit the weights or do arbitrary stuff outside.
Oh, it is allowed.
Yeah, both. You can do both. Yeah.
So this open question here, what do you want? You want a model that you cannot fine tune?
Yeah.
Or you want an attack that, oh, I can always fine tune it?
Either. I mean, like, I want to know, like, is it possible to
the
release?
existing work is neither of these things. It's like specific attacks and specific counterattacks.
Yes, exactly. Yeah, exactly. Something like this. Yeah, I want some kind of non-malleable sort of property where, like, I don't know, something's going on. I can use it, but I can't edit the weights or something. I don't know. But like, you know, people are working on this problem. And they're not cryptographers, and like I'm wondering, like, is there a crypto thing that feels like maybe?
Yeah. For one thing, a definition, right? Because obviously they can do it without it. So you want this not to add.
Yes, yeah, definition is a good point to start. Would be nice.
The problem still is that you want to give them some lot of like a model to work with, and not sitting and.
Yeah, exactly. I want to give you a binary, and I want to let you use the thing to do inference, but I don't want to let you change the way the thing works. Yeah. Okay. Okay. There's another area people have been talking a lot about. Feels sort of crypto-like. People call it something like compute governance, something like this. The idea of the question is we would maybe like to know where the chips are and be able to sort of have some exert control over what they're doing. You know, for example, the United States prevents NVIDIA from shipping particularly powerful chips into China. Like sort of, NVIDIA is not allowed to sell the best chips and have them be used in China because they're worried that then this will enable people in countries the United States doesn't like in order to train the best models. Okay. Whether or not this works or anything like it, the policy implications aside, there's a technical question here of, is there a technological method that we can use in order to try and do anything about this? Where a bunch of people are trying to think about, okay, what I'm going to do is I'm going to make the chip try and ping my nearest server for requests to be allowed to continue to be working. And if the request time is greater than some distance, then I know it's not, you know, in the country. And so then like on the hardware, I'm going to deactivate the chip, something like this. I don't know. People are in the machine learning space are like assuming the existence of various cryptographic primitives that may or may not exist and may or may not be vulnerable to replay attacks and other things like it. And so I would like some people like in this space to think about these kinds of things that people are proposing, because there's a very real world in which this gets built, whether or not we want it to, and it is built very, very poorly because the people who actually are skilled about it think that this is a hard problem, and as a result, they don't think about it. So I sort of would like to call attention to this as a thing that people are trying to do, and like we should have at least people sort of technically capable thinking about this.
Can you say again, maybe in a short sentence, what you would love for cryptographers to do?
Is this a thing that can happen? Like, can I reliably sort of do some kind of like very, very fancy DRM-like thing in a way that, you know, lets this be a thing that can work? Like, again, I would be happy with like a proof of impossibility of some kind of like, this doesn't work in this way, because like lots of people assume that it is. And so it would be nice to know, like, is this a thing that you could actually rely on?
So the idea here is it's like a post filtering.
Yeah, something like this, sort of like something on the chip that's going to like, decide whether or not it's allowed to be running at any point in time. Or I don't know. There's lots of things people are proposing. There's like a million proposals.
They'll put it in the hardware.
Maybe, yeah. Yeah. I don't know. But like people are talking about doing lots of these things. And I feel like lots of the people who are talking about this are not the crypto people. And I would like, people thinking about this.
Based on whether or not it's in China?
Based on, yeah, so they try and do location by sort of pinging the nearest server and check the round trip time. And if it's above some time, then it's like not physically close to my data center.
So these papers do that?
They assume the existence of things that talk about these kinds of things. So if you start here, this is a good sort of broad reference. There are like a number of papers that try and do things like this.
There's a lot of failed attempts on this when people are trying to do data locality.
Exactly, yes. There are a lot, like if you go back to the history of like, people failed to do this in crypto, with downloading media from like this is just a huge literature of
Sure, your data's in Europe.
yeah. There's lots of hard problems here, but like so like as security people, we like to think of we might look at this and go, it's not going to work. I'm not going to touch it. But like then what this ends up happening is the only people who start thinking about this are the people who are not educated about the problem, and then you end up with proposals that don't work that no one has things to look at. So I just don't want that to happen. Like I think there's whether or not you want the thing to exist, and there's whether or not the thing will exist. This might exist, and I would like people to think about it who have the skills to think about it.
They're missing the point. Why not to use digital signatures? Only something properly signed will be run, and keep the signing outside of China. Sorry, I'm missing.
Sure. Okay. Yeah. So there are lots of proposals you can try and imagine, but like suppose that you signed the thing to work once when it was in the United States, and then they just like sold the chips to China, and they like move them afterwards. You have to like make sure that like this isn't the thing that happens. Like there's lots of sort of yeah. Okay. I'm almost out of time now, so I'll spend maybe a couple of seconds on the last few things. There's something else people are trying to think of, which is a similar kind of thing, which is auditable training. There's a thing called proof of learning, which is like a nice paper that is not this, but it's like a nice like sort of idea of what I'm thinking about. But what auditable training tries to do is it tries to be able to give some verification, and Shafi spent some time thinking about this, of what happened during the training pipeline. And so maybe I want to prove I only trained on certain types of data. Maybe I want to prove I did not train on this other type of data. I want to be able to make arguments about this. Another thing in this direction is there are now starting to be regulations around if you have spent a certain amount of compute to train your model, you must report properties of your model to various government authorities. This is like a thing that exists in the world now. Is it possible to prove that I spent less than that in order to train my model? Like, could I sort of produce a model and along with it produce some kind of zero knowledge proof or something, I don't know, that says the total number of flops that went into training this thing was less than X. That's why you can believe me, I don't need to report this to you. Because like currently it's relying just like on good faith. Similarly, the government might ask the opposite direction.
Prove that you spend little time.
Yes.
Why is that important?
Well, so the idea is that if
It's like uranium, right?
yeah, the idea is like, suppose that really smart models could be dangerous, the government might want to know what they all are. And so they want to know like every model that has spent more than X compute that has to be reported to them. And so if I could prove I spent less than X, then I don't have to report. And so this is like a much like this is like proof of work, but like the other way around. Like I don't know how to do this.
Proof of laziness.
Yeah, proof of laziness. There you go. There's your paper title. And so yeah, like, is this a thing you could do? Like, I don't know. Like, there's like lots of these questions that feel like,
Maybe you solved a lot of other problems at the time, so you couldn't pay attention.
yeah, right. So there's lots. Yeah, there are ways of trying to like basically if you can say I only had access to so many GPUs and I can sort of show you that like something like this. Okay, I'll spend 5 seconds on the last couple things on indirect applications. One, we've talked about this a couple times in questions. Definitions. This is the thing that we're missing a lot in machine learning land that crypto has been very successful with. I think just producing definitions that are actionable and model something about the real world would be great. There's a nice paper, if you like, one problem I didn't talk about is something called unlearning. There's like, the world gets messy. If you want to see the problems in definitions, this is a very nice paper that like sort of talks about all of the ways in which definitions go wrong in terms of like what you actually want. And so it's just like, I would like to see more kinds of things like this that talk about real definitions versus what you actually want in practice and how to set things up in the right way. I think it'd be great to have more definitions here. The other thing that's sort of an indirect application is just like, it's like not that hard to attack machine learning systems. Like, it's like you compare the amount of work that goes into like doing like proper cryptanalysis to the work that goes into like attacking machine learning models. Like, there would never be a paper accepted at crypto where the attack was run the attack 5 times and it works one of them. Like, this is sort of like, this is true about the state of the world in machine learning. But like, there are papers at machine learning conferences where you run the attack 5 times and it works once, right? So like, it's like strictly easier to attack the things that we have available to us in machine learning land. If you're good at doing this like kind of thinking, I'm sure you would also be good at doing it in the machine learning space too. So this is to say, I think there are lots of fun questions. We need help in this space. The field is moving really, really fast. It's moving much faster than we know how to make things safe. And so I'm like trying to like recruit people to the cause of like, we're not going to be able to like reliably slow them down, but like maybe we can like at least like keep up. And so like, like keep pace to like make things not get any worse than they are now. I think one of the ways in which this happens is to have more security people start thinking about these problems, because I think it's one of the most important problems we're working on right now. So with that, thanks. And I think I'm out of time, so I'll take maybe questions afterwards, sort of going into the lunch a little bit. Thank you.
Great.
Thank you.